welcome you in the lecture series of random processes, detection and estimation. It is 39th lecture of this series. In the previous lecture, we have discussed about least square approach and linear least square. In this lecture, we will discuss about geometrical interpretation of the least square approach and constraint least square. The outline of this lecture are geometrical interpretation of the least square approach and constraint least squares. In the objective of this lecture, you will be able to explain how the geometrical approach helps to look inside into the estimator and how to handle the problem where the unknown parameters are constrained. Now, the geometrical interpretation of the LS approach. The geometrical interpretation of the LS approach helps to look inside into the estimator and also reveals other properties. Consider a general linear model S is equal to h theta, and if we denote the ith column of the H matrix is hi, the signal model can be seen as the linear combination of the signal vector h1 h2 to hp as S is equal to the vector h1 h2 to hp and the column vector h1 h theta 1 theta 2 to theta p, and it will be equal to summation I1 to p theta I into hi, and the least square error is j theta is equal to transpose of the matrix x minus h theta into x minus h theta. If the Euclidean length of a n is to one vector, xi is equal to transpose of xi1 xi2 xi n, then Euclidean length norm of xi, it will be the under root summation I1 to n xi I square, and it will be under root xi transpose xi. Then the least square error can be written as j theta is equal to square of the norm x minus s theta, and it will be the square of the norm x minus summation I1 to p theta I hi. The linear least square approach attempts to minimize the square of the distance from the vector x to a signal vector summation I1 to p theta I hi, which must be linear combination of the column of h. The data vector can lie anywhere in an n-dimensional space terms as r to the power n, and while all possible signal vector being linear combination of p less than n and must lie in an p-dimensional subspace r to the power n terms as s to the power p, and here in this figure n is equal to 3 and p is equal to 2. All the possible choice of theta 1 theta 2 produce signal vectors constraint to lie in the subspace s square, and that is general x does not lie in the subspace. It is observed that the vector s cap lies in the s square, and that is close to x in the Euclidean sense in the component of x in s square, and this is the error vector as x minus s cap. In other words, the s cap is the orthogonal projection of x onto s square. It make the error vector x minus s cap to be the orthogonal to all the vector in s square, and two vectors in r is to the power n are defined to be orthogonal if x transpose y is equal to 0. So using the orthogonality condition, we will have transpose of x minus s cap means error vector h1 is equal to 0, and transpose of x minus s cap h2 is equal to 0. Let s cap is equal to theta 1 h1 plus theta 2 h2, then we will get the transpose of x minus theta 1 h1 minus theta 2 h2 h1 is equal to 0, and transpose of x minus theta 1 h minus theta 2 h2 into h2 is equal to 0. On combining these two equations using a matrix form, then we will have a transpose of x minus h theta into h1 h2. It will be equal to transpose of 0 matrix, or you can say transpose of x minus h theta will be equal to transpose of 0 matrix. We get least square error as here theta cap is equal to inverse of the matrix H transpose H into H transpose X, and error vector epsilon is X minus H theta. Then we can have epsilon transpose H is equal to transpose of the zero matrix. The error vector must be orthogonal to the column of H, and this is known as the orthogonality principle. And the minimum least square error J minimum can be given as J minimum is equal to square of the norm X minus H theta cap, and it will be equal to transpose of matrix X minus H theta cap into X minus H theta. And I can write it as X transpose into X minus H theta cap minus theta cap transpose H transpose epsilon, and I can write it as H transpose X minus X transpose H theta cap, and it will be X transpose into 1 minus H transpose inverse of the H transpose H into H transpose. Now the constraint least square. In some least square estimation problem, the unknown parameters are constant. Let we wish to estimate the amplitude of a number of signals, but it is known as a prior that some of the signals are of the same amplitude. In this case, the number of parameters can be reduced to take advantage of the prior knowledge. If the parameters are linearly related, it leads to least square problem with the linear constraint and could be easily solved. Consider a least square estimation problem with parameter theta subjected to the linear constraint p r less than p. Let the constraint R independent. We can summarize the constraint as A theta plus B. A here is R is to P matrix and B is R is to 1 vector. And to find the least square error subject to the constraint, we set up a Lagrangian and determine the constraint least square error theta c cap by minimizing the Lagrangian JC theta transpose of X minus H theta into X minus H theta plus lambda is to the transpose of lambda into A theta minus B, where lambda is R is to 1 vector of Lagrangian multipliers. Now take the first derivative of this JC theta and put it 0. We will get theta cap, the least square error. It will be theta c cap. It will be inverse of the matrix H transpose H into H transpose X minus 1 by 2 inverse of the matrix H transpose H into A transpose lambda, and I can write it as theta cap minus inverse of the matrix H transpose H into A transpose lambda by 2, where this theta cap is the unconstrained LSE and lambda is yet to be determined. To find lambda, we impose the constraint so that A theta c cap is equal to A theta cap minus A inverse of H transpose H A transpose lambda by 2 is equal to B, and lambda by 2 is equal to inverse of the matrix A inverse H transpose H into A transpose into A theta cap minus B, and put lambda in the expression of theta c cap. We will get theta c cap is equal to theta cap minus inverse of the matrix H transpose H A transpose and the inverse of the matrix A inverse H transpose H A transpose and into A theta cap minus B. The constrained LSE is correlated version of the unconstrained LSE if A is equal to B. Then constrained LSE and LSE are identical. Let us one example. Consider a signal model Sn. When n is equal to 0, it is theta 1. When n is equal to 1, it is theta 2. And when n is equal to 2, it is 0. If we observe x0, x1, x2, find LSE. By this example, we will explain the effect of constraint on LSE. The signal vector can be expressed as, s is equal to h theta. H is 1 0 0 1 0 0, and theta is theta 1 and theta 2, so it will be theta 1 theta 2 and theta 3. And by this expression, the unconstrained LSC and signal estimate can be obtained as theta cap is equal to inverse of the matrix H transpose H into H transpose X. It is equal to the column matrix X naught X1, and S cap will be H theta cap. It will be the column matrix X0 X1 and 0. It is known a prior that theta 1 is equal to theta 2. Express this constraint in matrix form. We have 1 minus 1 theta is equal to 0. So A is equal to here 1 minus 1, the vector matrix, and B is equal to 0. Since H transpose H is equal to 1, we have the constraint LSC as theta C cap is equal to A transpose inverse of the A transpose into A theta cap. It will be equal to 1 minus A transpose inverse of the matrix A transpose into A into theta cap. By solving this matrix, we will get theta C cap. It will be x naught plus x1 by 2 and x naught plus x1 by 2, and SC cap H theta C cap, it will be x naught plus x1 by 2, x naught plus x1 by 2 and 0. Since theta 1 is equal to theta 2, two observations are averaged, so constraint S1 is equal to theta when n is equal to 0, Sn is equal to theta when n is equal to 1, and Sn is equal to 0 when n is equal to 2. The parameters to be estimated get reduced to theta only. On estimating the unconstrained LSC of theta using the reduced signal model would have produced the same result here. And so far in this lecture we have discussed geometrical interpretation of the least square approach and constraint least squares. This was 39th lecture of the lecture series of random processes detection and estimation. In the next lecture we will discuss a new class of estimation which is different from the classical estimation where the unknown parameter of interest is assumed to be deterministic but unknown constant. But in that approach, this new approach, we assume that the unknown parameter is a random variable whose relation is to be estimated, and this approach make a direct use of Bayes theorem and known as Bayesian approach. Till then, thanks for listening this lecture. Thank you.